All right, hello everybody. Let's go ahead and prove Euclid's proof that there are infinitely many primes. The proof is essentially what's called a proof by contradiction. We're going to assume the opposite. We're going to assume there are finitely many primes. In other words, there's only so many primes. And that's not so unreasonable, by the way. We get used to there being, yeah, sure, there's infinitely many primes. Why? I mean, we're getting used to the fact that there's only finitely many elements in the periodic table. Right? Like, it ends, and so that means everything in the universe seems to be made up of one of these elements. That doesn't seem to be infinite, right? So why should the prime numbers be infinite? Why shouldn't it be that after 2 million prime numbers, I've now got every prime number I need, I've got every number I need to be able to produce all the other numbers by multiplication. Right? Why shouldn't that be? Could be, but it's not. There are infinitely many primes, so we're going to assume the opposite. That is, that there are only finitely many prime numbers. And if there's only finitely many of them, I can actually list them out. Now, I don't know what they are, so I'll just name them. Let's say P1, P2, P3, and so on, all the way up to P sub n at some point, right? That n might be 2 million, but it would end at some point. Hey everybody, let's take a break from the example for a sec. The example I'm doing here is really just a single example, and there are literally infinitely more problems you can run into on a discrete math exam. And odds are good you'll run into problems you've never seen before and be expected to apply what you know to solving them. But if you don't understand the content, you have no hope. So, if you're taking a university, if you're a student taking a university discrete math course, and you're serious about not just getting a good grade, of course, yes, getting a good grade, but if you're serious about understanding the content, then go ahead and click the first link in the description down below and book a free call with me. Now, back to the example. Now, what I'm going to do is I'm going to produce a number that can't possibly be formed by those prime numbers. And so here's the trick. And this is a trick to this proof. Let capital N be the number P1 times P2 times P3 times P4 all the way up to Pn. So all the primes that exist multiplied together, so it's a massive number, plus 1. Okay? Then this n shouldn't be prime, right? Under my assumption is that P1 to Pn are all the primes. This number is certainly way bigger than all of P1 and Pn, so it can't be prime. Then n is bigger than all the primes, and thus must be composite. But we in another video we proved that every integer is divisible by a prime. So n must be divisible by a prime. But we know n must be divisible by a prime. Now here's the thing. If I've listed all the primes, P1 up to Pn, it must be one of them, right? That is, there exists some I in the set 1 to n such that Pi divides capital N, right? There must be one of them, must be some I somewhere, such that Pi divides N. But check this out. But then, Pi divides N, and Pi certainly divides P1, P2, P3, all the way to Pn, right? Because Pi's in that list, right? If Pi was the number 7, well, this product would be 2 times 3 times 5 times 7. Eventually, 7's in that list, right? If Pi was 11, well, it's 2 times 3 times 5 times 7 times 11, right? 11 is eventually in that set. that prime pi shows up in that list somewhere, right? Pi is somewhere in there. Okay. Hey guys, if you are looking for help with learning discrete math or proofs, I know they're tough, then make sure to subscribe. I'm literally going to be posting every example I have here for free on YouTube to help you learn and understand discrete math proofs. Back to the example. And so certainly pi must divide that product. And so pi must divide the difference of those products. This is a basic number theory thing, what we did earlier in the section. Pi must divide n, take away p1, p2, up to pn. Right? Pi must divide the difference of those two. If I take a multiple of pi and subtract another multiple of pi, what I should get is a multiple of pi. But what do I get here? I get n, take away this product of primes. Look at the definition of n. What do I get when I take away the pi's, the product of pi's from the n? I get 1. I get that pi must divide 1. A contradiction, since no prime divides 1. Every prime is divisible by 1, but no prime divides 1. Because what that would mean is that you would need a prime times some divisor d equals 1, where that d is an integer. Prime times divisor equals 1. Not going to happen. Okay, so that's my contradiction. Where's the contradiction? What does it contradict? What assumption did I make that gets contradicted there? The only one I made. Get rid of that. The only assumption I made is right there. Assume the opposite. That is, that there are only finitely many primes. If that's the only assumption I made, then everything else, that's contradicted by the contradiction I get to the end. Thus, there are infinitely many primes. And we're done. It doesn't at all show what those primes are or how to find them or anything, but it does say there are infinitely many. And you can imagine, you can do this proof with smaller numbers too. Like if the only primes there were 2, 3, and 5. That was all the primes there ever were. Well, the capital N is 2 times 3 times 5 plus 1. What's that? 6 times 5 is 30, plus 1 is 31. 31 happens to be prime. And so 31 is actually not a multiple of any of 2, 3, or 5. And that's all we've done. You can do this again. If 2, 3, 5, and 7, and 11 were all the primes there were, then the number n, which is 2 times 3 times 5 times 7 times 11 plus 1, whatever that happens to be, is not going to be a multiple of 2, 3, 5, 7, or 11. It is going to be but it may or may not be prime. It might be a multiple of 31, maybe. But it's certainly not going to be a multiple of 2, 3, 5, 7, or 11. Okay? I think that's it. We'll leave that there. Have a good one. Talk to you again. Hey, thanks for watching. Remember, what I've explained here is just a tiny, tiny example in the literally infinite space of problems there could be that you'd run into. So, if you're interested in really understanding this content, getting a good grade because you understand the content, go ahead and click the first link down below and book a free call with me, and let's talk about if I can actually help you do well in this course.